All right, here we are again for another biology video. This whole week we've been talking about this question that's on the screen. How does an adaptation arise? In particular, an adaptation for the Bajau people who have this ability to dive down really far, 70 meters under the ocean surface. And that's because they have a bigger spleen, a mutation that leads them to having this big spleen, which leads them to be able to dive down deep, right? So they have an adaptation. And so you've watched some ed puzzles and we've done some simulations, but we just specifically tried to explain how did the Bajau get their big spleen, right? And so I just want to show you my model and then how that kind of leads to understanding evolution in general. So you have to start with variation. In the original Bajau population, most people had normal-sized spleens, but there have to be some that have bigger spleens and some that have smaller spleens, right? This is part of the idea that sexual reproduction leads to variations, and so everybody's a little bit different, right? The bell curve. Most fit in this average category, but there's got to be some on the big side and some on the small side for evolution to work. So here is my beginning population. I'm just going to use these little circles to represent the people. I don't have to actually draw people. And then they have this red circle around the yellow circle to show their spleen size. So these are my normal spleen size people. But there are a couple that have a big spleen shown by the big circle, the big red circle around the outside. And then there are some people with small spleens, and so I didn't have any red circle around there, right? So the yellow is the person, and the red circle represents the size of their spleen, right? And this is the visual way to show how everything's going to work. Now, there's got to be a consequence. There's got to be competition. And so life with a normal spleen is tough. But if you have a normal spleen, you can manage to support yourself plus one child, right? This is, again, something we talked about already called the struggle for existence. There's always has to be competition for the limited resources. Now, if you have a large spleen, you can catch more food and you can support two children. And if you have a small spleen, you can only support yourself. You don't have enough, you can't catch enough food to support any children, right? So that's the basic rules of this little model that I'm going to show, just so that we can actually put some numbers to it. So here we have that original population again, some with big spleens, some with small spleens. But as the green icon in the corner says, small spleens have no children, right? They can't support any children. So in the game of evolution, in order for natural selection to work, you have to have babies. So if you don't have any offspring, then you actually don't really count in the whole thing. And we're just going to ignore the ones that have the small spleens. So 2 out of the 8 have a large spleen. As you can see, 25%. But then the normal spleens get to have one child. So all these normal spleens get one child. The large spleens get 2 children. And of course, part of the evolution requires inheritance. And so the normal spleened people have kids with normal spleens, and the big spleen people have kids with big spleens. Now, we have a new population, or the population is growing. However, the parents are going to get old and die. This is an unfortunate part of the just the universe, that at some point, the older generation has to go away, right? Because for evolution to happen, we have to have a long period of time. And so the original parents are going to go away. But we now have a new population, this new generation of the population, that has 4 out of the 10 individuals has a big spleen. So it started at 25%, but now 40% of the population has a larger spleen. These kids are going to grow up to have their own kids. And so here we have 1 baby from each of the normal spleens and 2 from each of the large spleens. But then the next generation, the original, or the second generation, I guess it is, those parents are going to then have to die. So we take away them. And we're left with 8 out of 14 that have a large spleen. Now we're up to 57%. And this is just going to keep going, right? And I think this is going to happen one more time, where the normal spleens have their 1 kid, but then the big spleens have 2 each. And then The parents have to get old and die again. And now we're up to 14 out of 20, 70% of the population have large spleens. And so it started at 25% and then went to close to 50, and now it's at 70%. And this will just keep going and going and going, right? As the big spleen people keep having big spleened children, 2 of them, compared to the one spleen children, or the one child from the normal spleen children. That's not making any sense, but you know what I'm trying to say. One child from the normal spleened people. And over time, the population changes, right? Maybe many generations later, another mutation happens, and one of those big spleened people has a kid with an even bigger spleen, and that kid, maybe they can have 3 babies. And so this one now is going to start the whole cycle over again, where having this one extra advantage is going to lead to more offspring. Meanwhile, the ones without the advantage won't have as many offspring, and over time, the numbers will increase and increase and increase again. So we go back to this original diagram of the bell curve. Most in the new population, most of the people have the large spleens, right? Because the people that were on this side of the bell curve, they're going to have lots of babies. And so there's going to be more and more large spleened people. Now, there's still some people that have normal spleens and some that have even larger spleens, as it says on there. But the people with the really small spleens, they are not going to be having children. And so their side of the bell curve is going to get smaller, right? And so over time, a little bit is going up there and a little bit going down there. And you get an overall idea that the bell curve is moving. And this is kind of something that we saw a week ago when we were doing the adaptation versus acclimation, right? The bell curve is just the standard bell curve is kind of the default setting, but then evolution starts to work on this, and natural selection starts to push the graph, the bell curve, in certain directions, right? Over time, the average person's spleen is getting larger. We can see this in all kinds of different species, but here are some examples of the way that natural selection is going to affect the bell curve. The one we just talked about is this one on the left with the horses, or a giraffe neck. I forgot I was going to go with giraffes, not horses. Giraffe necks have slowly been getting bigger and bigger, right? The giraffe ancestor had a regular sized neck, but having a slightly larger neck led to an advantage. So the ones with the larger necks over here, they are going to be able to have more babies than the ones with the smaller necks. And so it starts to move to the right, as the large neck population increases and the small neck population decreases. So that's called directional selection. The natural selection is kind of pushing the trait in one certain direction to get bigger or to get smaller or to become more red or darker fur or whatever it is that is the clear advantage, the trait that has the clearest advantage. But it doesn't always work that way. The one in the middle is called stabilizing selection. This is when both sides of the bell curve have a disadvantage and the center of the bell curve has an advantage. And a great example of this is human birth weight. The heavier and the bigger a baby is when it's born, the more likely it will survive, especially when we're talking about back in the day before we had modern medicine and babies died very young sometimes because of weird problems that are happening. But bigger babies have less problems, fewer problems. And so you would expect the bell curve to shift over, right? Because small babies are not going to survive as much. So on the small end, you're not going to have as many offspring. But there is this problem with the fact that the baby has to be born. And so if we keep making the babies bigger and bigger, at some point the babies will be too big to actually be born the natural way, to come out of the birth canal, right? There's only so much space to exit mom. And so at some point, being too big is also a disadvantage. So the biggest babies also are not going to survive, and therefore they are not going to have any kids of their own. But the babies that are in the middle are going to have the most chances of survival. They're going to be big enough to survive, but not so big that they get stuck and kill mom or kill themselves trying to be born, right? And so this is stabilizing, where the center of the bell curve is the clear advantage and being on the edges of the bell curve is not. Finally, on the right-hand side is one called disruptive selection. It's kind of the opposite, or it kind of mixes both of these. Just like directional selection, there are a clear advantage. In this case, we'll actually watch a video about this, about these mice. The mice come in two different colors. There's the light ones and the dark ones, but they also live in an environment where there's light rocks and dark rocks. So if you're a light mouse on a light rock, you have an advantage. If you're a dark mouse on a dark rock, you have an advantage. But if you're a medium color mouse, you don't fit in anywhere and you have a disadvantage. The ones that are in the middle here are not going to have a place to go, and so their part of the bell curve goes down, and you start to get what looks like two bell curves, right? Because the bell curve is being disrupted. It's being split into two different bell curves. And this is actually a really interesting example that, like I said, we'll watch a video about, because this might then lead to the evolution of two new species as the bell curves get farther and farther away from each other, right? But all of this is due to just natural selection. The ones with the advantage live, the ones with the disadvantage die, and then we can see this graphically as the bell curve kind of shifts and is being changed by natural selection, right? And so this story it works for the Bajau people, it works for giraffes, it works for rock pocket mice, it works for any species that has variation and then competition and inheritance after the winners have their babies, right? And that's evolution. So, of course, we'll keep talking about this more and more. Let me know if you have any questions.